you say something?
Es mejor que lo haga el técnico. Porque... Ah. Yo no lo he encendido.
Okay, let's start.
Yeah.
But she seemed ready to act. In Warsaw University.
For this talk. Hierarchical networks I studied. For the end, I tried pseudo Dennis. Hierarchy is made up from Greek. Or some that hierarchy was this read Wikipedia, but hierarchy was definition of in every dictionary. And what we can simply are hierarchical. So if I don't know, individuals want to be in hierarchical structure. This is still an open question. And the problem is that in a complex network we don't have one good definition of hierarchical network. Some people identify hierarchical network as trees, or hierarchy corresponds to the connections between agents. So I don't have enough time to present all of them. So it's a good moment to stop this introduction and to go to the results. Okay. Okay, so in the next part, I start with the definition of my models, and then I present you some results. Okay, so examples of hierarchical networks that are created from the top, and by the top I mean from one special individual who starts the growth of network, is, for example, societies united in common support for some charismatic leader, or companies or scientists who based their ideas on the most fundamental laws. Like it's good to cite Einstein, for example. Okay, so this is some picture of what I mean by hierarchical network. In this context, I have levels, and this level 0 is my top of the hierarchy, and I will be call this 0 level as the best hierarchy level. So the best means the smallest age. And in the course of time, the next agents, next nodes will be located at the worst levels, so levels 1, 2, 3, etc. And the main assumption of our work is that it's really hard to one person to know everything about network, about society. So we assume that newcomers are known just some fraction of networks, and this fraction of network will be represented by parameter n. So how it looks like? So we have set of m nodes, and in this example it's 3 nodes. And this is our tournament, and this is the tournament when the best wins. So the new agent looks at the levels of these 3 nodes, and he chooses one node which is the best, is located the best in the hierarchy. So in this case, this is node at the level 0, and he will be located on level h equal 1, so it's worse level than its friend. So this best level will be always just consist by just one participant. Okay, and we have.
Why is that a tournament? I mean, why is it a tournament?
We just call it tournament because we have some competition between this set of nodes. Because he randomly chooses 3 nodes, and from these 3 nodes he chooses the best possible node for him. So for him the best possible node is this one. So in this context this is tournament.
Tournament is a competition, right? You made a competition.
Yes, yes, but competition is between these 3 nodes because they are located at different levels.
Okay, interesting.
I understand in this example you say that what is you put a friend, you say that is located in the level h+1. The newcomer is located in the level h+1.
Yes, because
So what was the original people?
I understand this is a model to grow.
yes, it's a growing network. So
Hierarchical tree or something.
But understand, the initial people say it has h=2, knows 3 people. Of course, he knows the CEO of the company, h=0.
yes,
And now the newcomer is added just below the CEO.
yes, because he knows him.
But you must assume that everybody knows the big boss.
No,
So
no,
all the new people will be arriving at the higher level.
no. This is newcomer knows set of nodes, but not this set of nodes is not equal for every newcomer.
Okay.
So
for
this one,
to have friendship with
it were these 3 nodes, but for other one will be, I don't know,
Yeah.
this 3 or something like that. So it's not that he always knew this one and this one and this one. It will be really boring model if we assume something like that. Okay. So you saw already that I have 2 models, and these models are different only because in model C I have constant number of participants in time, and in model P this number of participants is proportional to time. So in this case, during the time when network grows, this is decreasing fraction of network size, and in this case is constant fraction of network size. Okay, so we wrote simple master equation to describe occupations of levels in network, and our initial conditions are that in the 0 time step we have just 1 node at level 0, and at all higher level is no nodes. And in the simplest scenario, when number of participants is equal 1, so this is the random choice, number of nodes at levels grows as logarithm to power h. And as you can see, the levels which appears later grows faster. Is one of the interesting observations from this model. And similarly for different m, we also observe logarithmic growth of the first hierarchy level. We didn't solve analytically master equation for any h and any m, but we integrated it numerically, and as you can see, this numerical solution fits really well to computer simulations, and as I mentioned before, the levels which appears later grows faster. And what is also interesting, the distribution of levels is Poissonian with mean proportional to logarithm of time, and this is only for m equals 1, and for m greater than 1 we don't observe this behavior. Okay, so what about when these hierarchies appear? So in this random case, we observe that this time of birth of next levels is proportional to exponents of h, and for m greater than 1, the hierarchy growth is slower than in the case of m equals 1, which is represented by this
So
circle.
what was now the characteristic growth time?
No, tau was hierarchy birth time, when the first time hierarchy appears. And once more we have for tau 2, so time when second hierarchy level appears, we have analytical solution which fits well to numerical simulation, but for higher levels we have just numerical integration, which is not perfect but follow the trend. So and so next thing we try to calculate is number of hierarchy levels in time, which in this model is growing. And for m equals 1, the growth is logarithmic. And similarly as number of hierarchy levels in time, also the average hierarchy level grows logarithmically.
Will you comment on the steps that appear there?
For the steps are related to the because in numerical simulations we don't have levels equals 1.5 or something like this, so this is related to the numbers from simulation. And don't if we have smaller legend here, we see that this is for 1, 2, 3 and so on, so it's like grow for every number.
So this is simulation.
Yes, here is simulation. And here is also simulation, but for m equal 1, the time when next levels are created is smaller, so this step-like behavior is not so evident.
This must be something like a smooth in the data, right? When you have 5 plateaus up to level 5, so you cannot have anything. I mean, those points in the diagonal, you have plateaus.
Yes.
These plateaus are integer numbers.
Yes.
But that's an average.
Yes, this is an average, but here, okay.
I get it.
Okay, because when we have large age, the time between next between we can observe next level is big, so this step-like behavior is small, because here is the time interval when for some realizations we have this level and for some we didn't have, but here in all realizations we have this number of levels.
So there's a well-defined time
Yes.
to create a new next level, but there is some spread. And then when you average, you
Yeah,
reduce
so
it.
we have, because of that we have something like this, which is more evident for greater m.
So you are measuring time. Time is just the number of elements you are adding. So each time, new time is a new element added.
Yes.
So it's not like in other simulations in which you have, for example, you add n new
No,
elements.
no.
It's not a unit of time. So
No, because this is growing network, so
it's growing linearly with the number
Yeah.
of elements.
okay. So for phi model, we also can write some master equation, and if we assume continuous time, we get this solution for n1 and n2, and for big time, when t is greater than 1, we can write these approximations, which are really nice, and these approximations clearly show that the system is monopolized by two first level under the root. To get n3, we can numerically integrate master equation, and when we compare these results with computer simulation, we see good agreement, and this is plateau for h, which confirm our approximated results. So these two first levels grows linearly, but after some initial time, this third level stops to grow.
What is the approximation? What do you approximate?
We approximate these solutions for t goes to infinity, and for t goes to infinity, this is just...
But before you had the exact solution.
Yes, yes, because we need exact solution to compare
This is the exact one.
this with numerics. It's because if we don't
Still
have...
you have a discrepancy for a small time, right? For short time, you have discrepancy.
Yes, yes, but it's because here this time is shifted one step to the right, so this lines goes to 0. So in logarithmic scale, it practically goes to infinity. So this is the reason. We just should cut this line here because it doesn't make sense. Okay. And to compare these two models, this is the occupation of levels for the same number of nodes for tournament, and as you can see in first model, number of levels is bigger, and in the second model, these two first levels have most of the practically whole network is in these two levels. And we can also calculate the number of hierarchy levels in time. So as you can see, after some time, the number of levels stop to grow because these two levels are most important ones. And similarly, average hierarchy level, when times go to infinity, it goes to 2 minus alpha. So it's constant value for different values of alpha, and these peaks are related to this initial drop of number of levels. Okay, so once more, a summary. This is the picture presenting comparison of these two models, and main conclusion that if nodes possess more information about the networks, the growth of hierarchy levels is slower, and when nodes knew about fixed fraction of existing nodes, then after some time hierarchy growth slows down to a complete standstill. So, this is thank you for your attention.
Any other questions?
From the when you wrote the tree, I was thinking if you were talking about general networks or about trees. But in fact, you are talking about neither of them. And I don't see the importance of any link. I mean, you have levels populated by
Yes,
agents.
because
I mean, I don't see any importance on the network nature of
as
this thing.
a network, in the context that I can write things, but we studied only the population dynamics. So you're right. In my work, links are not important at all. Because if node is located on some level, he stays there for the end of simulation. So if I assume some interactions or things like that, then the links can be important. But in this context, they are not important.
Can you explain a bit more the fundamental motivation? So is there any system you have in mind behind this? Because you already noticed that people associate, for example, economic hierarchies with it, but would you be able to motivate those two different models a bit more in that context? Or what you have in mind by introducing hierarchy this way?
Our first motivation, and this was motivation because we had hoped that we can have some real data to compare with results, was this example about companies. So how companies grow in time, but because of many factors, we didn't have data. And so
irrespective of whether you have data or not, what would be can you link a bit your growth model to what you had in mind, how companies starting by good promising initiator, what that would translate to?
Yeah, it was, so first you have one person which, have some investor, have money, he start company, he hires some friends or good workers or so on, and when someone wants to be hired, then it's not ideal situation, but it's like sometimes you can find information about when you can go to find a job in internet or paper or something like that, but usually it's because of friends of your friends and so on. So if you know someone who is good situated in company, you go to this person, not to the lowest one in hierarchy. So this was the motivation of this set of members and this tournament where the best wins.
Would be nice if only I need to know a CEO.
Yeah. If you're starting your studies and you know some professor, you can be PhD in one day. Yes, it will be nice, but it's not really true.
When you talk about hierarchy, and this is the plot, you usually think something which is pyramidal. Okay, there are more people at the bottom, that at each level there's more and more people. But it doesn't happen in your model for hierarchical. You look at the final, mostly in model P. Model P, I don't see any hierarchy there. I mean, I can see levels, but I don't see hierarchy.
Yes.
In the sense of most populated.
In model P, yes, but in model C, model C it's pyramidal because the higher level grows faster. So
yeah, well, in model C, yeah,
eventually. So this is the pyramid
but not in the
structure, but in model P, no.
When you talk about network, there is no real network here, right? That's what I need to say. There's no network.
Yeah, Yes,
So
yes.
you can study properties of networks here, this and that.
Okay, it's, the concept of network, we use this only when we consider these moments when newcomers join network. Because
Yeah, but you don't
it's
need,
some-
you don't need links
yes,
are not
it's
used at
some
all.
virtual link between these two.
But this link is not used at all.
Yes, yes.
Never.
In this model, no. But at the beginning, we thought about some
Okay.
network statistics. But
There's no- I don't see any network here.
yeah, so yeah, I agree. It's no network here, but we can draw some links. It's not changing anything.
Any other questions?
Yes, all this, during all this talk, I was thinking some models we studied some time ago in a very different topic, which is biological evolution, and in which the new species are evolved and are, appear, and usually they are attached to the newest node. So new species are at the bottom of the hierarchy. Then you grow evolutionary trees. But there are models in which instead of being attached to the newest species or evolving from the newest one, sometimes there is evolution of some of the oldest species. Then there are some models in which they attach to other levels. It's very different, but depending on the rule, in all the cases I've seen, you get something like a logarithmic, so number of elements grows logarithmic with time, which is with the number of elements. This is what you get when you have a, for example, if you grow a tree just by choosing at random one of the leaves. This is what models you get. But there are ways, in some cases, you can, this process accelerates if you choose not to attach to the lower level of the tree, but to some intermediate level. And this has some biological implications. Have you seen any cases? In all the cases I've seen, all the growth of elements with time is logarithmic or logarithmic to some power. Have you seen some power law of the occupation? In some biological models, this happens. So the
Yeah, I
growing
know,
in
but,
time has a power not with the logarithm of time.
yeah, but here we have. I didn't see any power of behavior here, and maybe if we have more than one individual per time step. I don't know exactly, but I think in this kind of model, it will be hard to observe the power of behavior. It's like I don't have intuition how to improve this model to switch from logarithmic behavior to exponential, not to exponential to power of behavior. But also in biological networks, the more common approach is not from top to the bottom, but from the bottom to the top. So we have a group of initially equal individuals, and they fight to be higher in hierarchy in group or something like that. Like, for example, Bonobo model.
There are more questions? We can go again.